I'm changing the software I use to record these lectures, all the time, and so I have some bugs to work out. I'm always working on my software. Okay, so lecture 6.2, first order systems in transient response, is going to get kind of into the nitty-gritty of transient response for a very specific type of system, a first order system. And these systems have input-output differential equations of the form of equation 6.2. So we have a time constant, tau, so that's just comprised of some parameters of our system, maybe the mass of the system, maybe the spring, maybe the resistance or capacitance, for instance. And we have the time derivative of the output plus the output. So it's first order because it's got the highest derivative being 1. And it's linear, obviously. And the right-hand side of the equation has time derivatives of the input u, and this is the forcing function, of course, f. Good. So systems with a single energy storage element, such as those with electrical or thermal capacitance, can be modeled as first order. And we'll do a lot of examples of first order systems throughout. And I did add an example to this lecture today, so we'll see one of them today. The characteristic equation yields a single root lambda equal to -1 tau. So the homogeneous solution for constant kappa is y homogeneous of t equals some constant kappa e to the minus t over tau. Okay? So that's our usual bit there. If we wanted to go through and look at what happens if we put in a specific input, we could do our particular solution and our total solution and then apply the initial conditions to that. But what we're going to do is we're going to take a little bit of a different tack this time and see how we do. So we're going to look at the free response first. And the free response of the system, as we recall, is its response to initial conditions and no forcing, right? So initial conditions, forcing functions, the right-hand side of the equation is set to 0. And this is useful for 2 reasons. So first, it models perturbations of the system from equilibrium. So if you are to start at an equilibrium and you perturb it from the equilibrium and let it go back to its equilibrium, then we'll see a free response. And also from superposition, the free response can be added to a forced response to find the specific response. So if you wanted to sum up the free and the forced responses, you can do that. This allows us to use tables of solutions like Table 6.1 to construct solutions for systems with non-zero initial conditions with forcing. So let's look at Table 6.1 for just a moment and see. So what I've got here are characteristic responses. I also have total force responses. I'm gonna like, this is kind of it's not cheating. It's just like the solution to a very general problem. I don't mind if you guys use this right-hand column of this table, but I would encourage you to learn how to use the second column first, and that's what we'll do in the example today. We'll use the second column because when we get to second order systems, you only get the second column just because this column just gets too massive and we just don't write it down. So I encourage you to start using the characteristic response because you'll use it in the same way for first order systems and second order systems. So we're going to learn how to use this column of the characteristic response column. But you see how we have a row for each input, so the unit impulse, unit step, and the unit ramp, and the characteristic response of the system, which is to say the response of the system, the force response of the system with the forcing function set to the input. Okay, so we'll revisit that. So we know we can construct these solutions using the free response and the forced response that we can construct from these tables. And now we just need to know what the free response is for a first order system. So the free response is found by applying initial conditions to the homogeneous solution. With initial condition y of 0, the free response is just this. So the initial condition multiplied by this hopefully decaying exponential, assuming your system is stable and tau is positive. Okay, so that's our free response. And now we need to look at forced responses, okay? So we have this idea that we can take our free response, which we already have, bang, equation 6.3, and we can sum it up with the forced response, but we need to find forced responses from the table, and or from the table would be my recommendation. So that's what we're going to learn how to use. Well, we need to kind of investigate first, how do you construct these forced responses? And then we know that for any given problem, we can just sum up a forced response and a free response for it, and get the specific response is one thing to call it. So let's look at the step response. Notice there were 3 different singularity functions that we mentioned: the unit impulse, the unit step, and the unit ramp. We're going to look at the step response, unit step response, and we could also go into the Dirac delta function, the unit impulse function, and the unit ramp function, but I decided to just focus on the unit step function and just give you the results in the table for the others. So, but you can develop them in a very similar way. So in what follows, we develop forced response solutions, which are the specific solution responses of systems to given inputs and 0 initial conditions. In other words, all initial conditions set to 0. If we consider the common situation that B1 is 0, what does that mean? So B1 is this term. So oftentimes we don't have a term that has the derivative of the input show up in our differential equation. Sometimes we do, sometimes we don't. It just depends. Frequently we don't, though, and we just have this scaling of the input u show up. And if we have our input being the unit step function scaled by some constant k, the solution to equation 6.2 is what? Y forced of t equals that constant that scaled our unit step function, so this k, times b naught. So b naught is right here, right? That's b naught. So scaling our input, times 1 minus e to the minus t over tau. So the non-steady term, so this term here is steady, right? It's just a constant times 1. So that's not changing as time increases. This other term gives us something that's varying with time, right? So it's not steady. So the non-steady term is simply a constant scaling of a decaying exponential. So this k b naught scales this decaying exponential, but eventually that all goes away. Okay, so a plot of the step response is shown in figure 6.1. As with the free response, within 5 time constants, we see the transient die out, 5 to 6 time constants. So let's look at this. So what I plotted here are, I guess, 3 responses, and I also showed the unit step inputs. These are all step responses. And this is the forcing function. So this is the factor out in front of the unit step function. So it's equal to k b naught, the scaling of 1 for the unit step function. And then we have first the free response. So the blue line is the free response, which is the response of the system to the initial conditions alone with no forcing function at all. So that's the blue. The red line is the forced response. So say you started out with 0 initial conditions all set to 0, and then you put in this forcing function, KB naught US, unit step function, and we would get out this response. So it starts at 0, and it goes up to KB naught exponentially. Now, if you had a system that had both that initial condition that we considered, why not, and also the forcing function, the unit step, and you wanted to know the solution to that, you could simply add them. And that's what the green line is here, the sum of them. So that's what this line is. And that would be one way to use superposition to construct the solution. And we can do, I'll show this in this example now. So now that we've got these characteristic responses to these systems, we can use superposition, free response, forced response, etc., to construct our solutions pretty easily. And I'm gonna just kind of ignore this column because it's like cheating a little bit. It's really not. It's just like I want us to be able to use the characteristic response column because in the second order systems you have to. So yeah. Okay. Wonderful. So the response to all 3 singularity inputs are shown in the table. These can be combined with the free response of equation 6.3 using superposition. So equation 6.3 gave us the free response, so we can always combine that with all these forced responses and go from there. Results could be described as bitchin', and you guys already have seen it, but it's worth seeing again. Bitchin'. Pretty awesome. Okay. I strive to one day be as cool as her when she was wearing this and had the eye makeup. It's like, she's pretty cool. Wish I was that cool. maybe one day. Yeah. I think I'm headed in the wrong direction though. I'm like over 30. Don't think you get a lot cooler after 30. Buy a Harley? Yeah, that always works. Yeah. I feel like, a moped would definitely do it.
Practical.
It's practical. I could wear my Dockers and ride in on my scooter.
Need one of those 3-wheeled
Oh man. Yeah, have you guys seen somebody on this campus has it's like a bicycle, but it's an elliptical?
You can check them out at the rec. There's 2 of them.
Oh man. Imagine how cool that would be. Riding an elliptical around campus. That is wild. Okay.
You don't crash that one.
Yeah, I feel like that would be very dangerous. I would definitely crash. I crashed a bicycle.
Just flip forward and stop, because the handles are long enough to just sit on one edge.
Yeah, I don't feel like you would though.
No.
Okay, yeah, this is like bringing back trauma for me right now. Whew, PTSD a little bit. All right, we need to move on. Hopefully I don't have a flashback and go crashing to the floor.
Please don't.
Remember when I was bleeding all over my laptop during class last semester? I was worried about my laptop. Okay, let's do this example. It's pretty easy. So consider a parallel RC circuit with input current IS is equal to 2 times the unit step amps. So it's 0 amps and then it's 2 amps. Right when we start the clock, time equals 0. An initial capacitor voltage of VC of 0 equals 3 volts. Resistance R equals 1,000 ohms, and capacitance C equals 1 millifarad. Proceeding with the usual analysis would produce the input-output differential equation given here. So we've got time derivative of VC, we've got VC, and we've got our current source there. So I don't know, I didn't get a chance to recompile, I added this, but use the table, what is it, 6.1? Table.
Yep.
Table 6.1 to find the output, to find VC of t. Okay, so that's our problem. So first step is we notice, first of all, that our input, u, is equal to is. This is just a good thing to note. And our output, y, is vc, right? If we just look at the differential equation, we can see that those two are the case. So is is the input, vc is the output. Great. 2, we should rearrange, the ODE. And we need to rearrange it to be in the standard form because we're going to use the tables. And if you're going to use the tables, you have to rewrite your equation in standard form. So the standard form is going to be RC, and do you guys want to switch over to y now? Let's switch over to y. dy dt plus y equals r times, instead of is, let's use u. So that's our standard form. We can identify that tau, our time constant, is RC, and also identify that our B1 is 0, which is to say there's no derivative of the input term here, and B0, or B0, is R. And I finally identify the fact that the forcing function is just R U, which is equal to R, and U is, the input is 2 times the unit step function, right? So 2R unit step function. Cool. So we just rearranged and we could just identify all those things, right? Just from the standard form of the first order ODE. Okay. So then let's use superposition in the table like it was suggested that we do. So let's find the free response first. We always find the free response for a first order system to be just equation 6.3, right? Given there. So it's just y naught, so y free of t is equal to y naught times e to the minus t over tau. We've already identified what tau is. Y naught was given as being 3, right? 3 volts. So I'll just put it here, equals 3 e to the minus t over tau. And now we need to find the forced response. Well, let's find the characteristic response and then the forced response. Well, it's too easy. We'll just do forced response. Okay, so the forced response is, let's think about what we have here. We have a unit step input, so this is what we're using. We want to find the characteristic response, and then use that to construct the forced response, right? So we know if we put a unit step in, we're going to get that as our response. So let's write y characteristic, we'll say, ch. T is 1 minus e to the minus t over tau. And this was using table table 6.1. And we know that from the forcing function being equal to 2r times the unit step function, we can say that the forced response is just going to be 2r times 1 minus e to the minus t over tau. So we have our forced response now. We used the characteristic response, and we used superposition to construct the forced response from it. And finally, 5, we can say the like specific or total or something like that response, which is VC of t or y of t, whichever you'd like to call it, equal to the sum of the free response and the forced response, right? Forced response of t equals, so we just need to add those two terms, so 3 e to the minus t over tau plus 2r 1 minus e to the minus t over tau. You could rearrange that if you like to get the two exponentials together. It's probably a good idea. So it would be 2r plus 3 minus 2r e to the minus t over tau. Notice that we didn't have to do a whole lot of work to come to that solution because we used the table and superposition. So that's what we're going to do also for second order systems on Friday. Okay, see you guys then.